Hello everyone, and in this video I thought we would go over like kind of an introduction to assembly. I want to make some videos on shell coding, so this would be a good introduction. And I also wanted to explain kind of some of the stuff we saw in last video, because I didn't explain it all as well as I could have, and making a separate video would be probably really beneficial for you guys. So, not to reinvent the wheel, but we're going to make a video on basic assembly, but we're actually going to write some stuff, and we're going to step through a program with GDB and find out how everything really works. So I have some notes here that I wrote down from when I was learning about our registers. So there are 16 general purpose registers, and they all have names, like 3-letter names. The most common ones are RAX, RBX, RCX, and RDX. And these are the 64-bit registers, which is exactly what it sounds like. They're 64 bits. And then each of them also has lower segments. So RAX has EAX, then AX, which is 16 bits, then AH and AL, and so on and so forth. RBX is EBX, BX, BH, and BL, and so on and so forth. Then there are 4 more: RSI, RDI, RBP, and RSP. RBP is the base pointer. RSP is the stack pointer. If you're not familiar with those, all they do is they're just exactly what they sound like. Points to the base pointer, and then the stack pointer. Stack pointer points to the top of the stack. They're used for the base pointer is used for like stack frames and other things like that. Then comes R8 through R15, more general purpose registers. And here I have that if you have X be the number, whatever number 8 through 15, then R8 is a 64-bit version, R8D is a 32, R8W is a 16, and R88 is the 8-bit version. And with these 4 registers, you also have an upper 8 bits and a lower 8 bits, but you don't for the other ones. And then the R flags register, 32 bits reserved, and then the remaining 32 bits is the E flags register, which will basically hold things like your 0 flag, your carry flag, things like that, which we can look at later if we want. And then .text is where the executable code goes. We'll look at that in a second. If you ever use syscalls, the number goes into RAX, and then the arguments are passed in the order of the first argument goes in RDI, then RSI, RDX, and so forth. So, moving on to this program, I have a simple program here, and what we're going to do is, this is NASM assembly, so we're going to step through this program in GDB, and we're going to kind of learn how everything works, so that you can see how operations actually happen with the registers and things like that. So line number 1, we declare the entry point of the program for the linker, which when you're using NASM has to be this _start. Section.text, this is for our executable code, and now we declare the entry point, and we actually dive into what we want it to do. So the first thing we're going to do is the move instruction, and all the move instruction is going to do is you can either move an immediate value like this, like 1, into a register. You can move a memory address into a register. You can move a register to a register, or you could dereference memory and move that into a register. So in this case, we're going to move an immediate value 1 into RAX. So this is Intel syntax. So as I've written, it follows this operation, which is move, then the destination, which is where the source is going to go to. So in this case, the source is 1, the destination is RAX, and the operation is move. And now So now the value 1 will be in RAX, and then our next instruction is going to XOR EAX EAX. And if you're not familiar with XOR, it's basically just exclusive OR. So if you have a 1 and you XOR it with a 0, you'll have 1. If you have a 0 and you XOR it with a 0, you'll get 0. And that's because it's exclusive OR. So basically, if you XOR something with itself, you're just going to 0 it out. And I put this in here because when you write shellcode, which I hope we'll do on this channel, the fastest way to clear a register is to XOR the 32-bit version of it, which is actually 1 byte shorter than XORing the 64-bit version of the register. So if you ever needed to clear the EAX, which you will a lot for writing shellcode, this is the fastest way to do it. And it will, you can use EAX because it will 0 extend the remaining 32 bits. But if you were to do like XOR AX, it would not 0 extend, meaning that the rest of the register wouldn't be cleared. So you have to use EAX if you want to 0 extend. Next, we're going to move 12 onto the stack, just pushing an immediate value. Then we're going to pop, and this will be in hexadecimal, by the way, when we see it in GDB. We're going to pop 12 into RAX, and the way pop works is it just takes the last thing that was pushed, in this case 12, and it moves it into the destination. So in this case, you don't see the source, but the source you have to look up here to this line to see that it was 12. And now 12 will be into RAX again. We're going to add 12 to RAX, so RAX is already 12, and now we're going to add another immediate value to 12, to RAX, so that'll equal 24. Again, operation, source, and where it's going, the destination. Once again, we're going to clear RAX. Then we're going to move bracket message into RAX. And you notice down here, I've defined what message is. It's a DB is defined byte, or bytes, and I have 0x11, 0x22, 0x33. So what's going to happen is, when you use these square brackets, you're going to dereference the memory address of this variable. So you're going to take the actual value, this, and you're going to store it into the destination, which is RAX. On the other hand, when you do just the name of the variable, you're just going to move the memory address into RAX, not the actual value. So that's a very important distinction. And then actually, this will segfault afterwards because we haven't exited the program properly. And like, it's kind of like C, where you return 1 at the end of your main function. So I'm just going to do that right now. Go down to the bottom here. And let's do it like we're writing shellcode. So what we would do, we would clear the register. Then we don't want any null bytes, so you can't do like move 60 into RAX because that would produce null bytes. So what you have to do is, you could do this. And all this is doing is exactly like this line right here. Add 12 into RAX, except this time we're moving 60 into RAX, which is the syscall number for exit. So we're actually calling upon the kernel to help us with our program. In this case, we're going to use a syscall, a system call. And then, the syscall number always goes into RAX, by the way, which is why we're doing that here. And then what we want to do is the next argument is a status code, which goes in RDI. And we can exit with the status code 0 for no errors. And the easiest way to do that is to just clear RDI. So RDI has 0. Okay, and then all we need to do is make the actual syscall, which will look at whatever's above it. It'll find the appropriate arguments. Remember what we said, that the syscall number always goes into RAX, and the following arguments go into RDI, and then the other registers continuing from there. but the first argument goes in RDI, which is just 0 because we're storing it with itself. Then we make the syscall and it'll exit for us. So save this. We're gonna assemble it and link it. Oh, hang on a second. Syscall. Sorry, I missed an S there. You guys probably already saw that. Link. And if we run it, nothing will happen because it doesn't really do anything. But underneath the surface, it's doing a lot of stuff. So yeah, it doesn't do anything, but if we examine it with GDB, we can actually look at what's going on. GDB for quiet, because it has a bunch of stuff that it prints out when it starts. TUI, which is text user interface, which I really like. And then our executable. Okay, so now we're in GDB. So we're going to set our disassembly flavor to Intel, which is the syntax we are looking at later. I can maybe make a video about AT&T. I mean, most people use Intel. Intel is generally the easier one to use for obvious reasons once you see AT&T. We're going to have a breakpoint at start, which again is the entry point for the program. You run the program and we hit our breakpoint, so now we're going to look at everything. Lay out the registers. Lay out the assembly. Oh. Okay. And now you can see we just have all our assembly again, except this time in GDB, which looks more like disassembly. So the first thing we're going to do is we're going to move one into EAX. So let's keep an eye up here. This is where we have our registers. So if we do a step instruction, we see that the immediate value 1 goes into RAX. All very good. Now pay attention, XOR EAX is going to clear RAX, so that's going to become 0. Step instruction, and you can see it becomes 0. Now we're going to push the value 12 onto the stack. This is just 12 in hexadecimal, I'm sure you know. So step instruction. And now we can't see it, but we can examine it with GDB. And you see there it is. We've looked at the stack pointer and you can see it's pointing to the value C, which is 12. So you can see the RSP is pointing to this memory location, and we just examined that memory location as hexadecimal. Now pop RAX should take the last thing that was pushed, 0xC or 12, and put it into the destination, which is RAX. So step I, now RAX has the value 12 or 0xC. Now we're going to add 12 into RAX. So RAX is already 12, so adding another 12 should make it 24. Indeed, it's 24. Now we're going to clear the register again. Remember, it'll 0 extend. There we have it. Now we're taking this memory address, we're dereferencing it, and we're moving it into RAX. So if we examine 3 bytes of the variable message, Sorry about that. Sorry, I forgot you had to use the ampersand here. I was a little puzzled for a second. But you can see message clearly has 0110x22 and if you look, it's stored at this memory address, and here is the memory address that corresponds with it. So we're going to move this into RAX, and you can see it got put into little endian, but that's fine. 112233. That's just to show you how you can dereference memory locations and move it into and work with registers that way. Now we're going to clear the register again. You notice RX became 0. We're going to move the absolute value, move abs, address into RAX. So if you remember from our assembly, this line was move RAX, comma, message. And with the no brackets, all message is the memory address that it's stored at. And you can see right here is 0x6000E0. So we're going to move literally that address into the RAX register. Step instruction. And there it is. The address of our variable is in RAX. Now we're going to clear it again. We're going to add an immediate value of 60 into RAX. We're setting up our syscall. So now that the syscall number is in RAX, we need to give it the status code, which is 0. And to give it the status code, we need to put the value 0 into RDI. So we can do that by just storing RDI with itself. You can see RDI is already 0, but sometimes when you're writing shellcode, you don't know whether something has a value or not, so it's always a good idea to just clear it, just in case. And now we're going to exit. And you can see the program exits normally. So this was a kind of introduction to assembly. There's a lot I didn't cover. I'm sure I'll leave it to you guys to kind of learn about, you know, maybe you don't know what a quad word is and you have to look that up. Maybe this is the first time you've encountered a bitwise operator. Maybe you don't know what the stack pointer is yet, although I kind of touched on that. Maybe you don't know what the RIP is, although I did that in my last video. But whatever you were confused about, just, you know, Google, keep learning on your own, and hopefully next time we'll begin writing some shellcode, and then I'll get back to doing VulnHub boxes. Let me know if there's a specific VulnHub box you wanted to see. As far as what I was thinking maybe I really like the box Oracle, Sedna, so a couple of those. But until then, I'll see you guys later.